Mr. Chairman. So today I have a pleasure to present this multi-wave waveguide technology, multi-layer waveguide technology, a new solution for automotive radar antennas. It is a pleasure because it's not often the time that you have the opportunity to officially release a new technology, something that we really believe has a significant impact and is also extremely mature and ready to be deployed. So I want to spend a second just to acknowledge the other author, Abbas Bazouk and Stefan Carson, especially Abbas, since he's the mind and muscle behind this fantastic work. Unfortunately, he's not here to present since he has an even more pleasure instance with the honeymoon. But I'm sure he had a presentation a bit more technical in UCAP, so you can also refer to that. So a very quick introduction to the agenda. So we'll start with a bit of a background on the company, the technology, and overall our automotive offering, since this is the topic of the session. And then we'll enter in the details of multi-layer waveguide technology. We'll touch upon the key benefits, introduce a demonstrator, and wrap together the conclusion. So as a quick overview, Gapwaves is a small company based in Gothenburg, Sweden, has been founded in 2011 by late Professor Percival Kildall, and is based really on the technology that was developed there, the Gapwave technology, and has been since focused on commercializing such solution and bring it to the mass market. It was listed on the Nasdaq First North in 2016, and since then has, of course, worked and specialized in millimeter wave antenna solution and bring forward extending the strong partner portfolio and bring this solution to market. The technology at the core of our company, again, is the Waveguide Technology, and it's really focused on combining manufacturability, cost, and performance in one single package. So it's here there is an illustration on the right-hand side to simplify. You might have seen it already. The top right corner is Waveguide Technology, the most classical and most well-known technology. They provide very nice performance, and we've seen them becoming very attractive recently. However, they generally suffer for very challenging manufacturing. So here is an example. If you were to realize in two parts, which is basically always the case, when you put them together, if you have any type of defects putting together, they will just dramatically die, and that it's very tough from a manufacturing point of view. Waveguide Technology instead is based on replacing basically the walls in the most simple sense with EBG or a metamaterial, or essentially this repetitive post on the side, which have some particular dimension that prevents basically the wave from leaking and maintaining the performance that you get out of waveguide with the manufacturing for practical consideration. So it's really designed for high volume, for reliable construction, and to be flexible in manufacturing, of course, cost effective. So the objective obviously is that one to enable high performance to the mass market over there. So obviously, since we've been working millimeter wave frequency, automotive application has been a very good match. There is a kind of a sketch of our timeline since we've been founded and started, actual operation in 2016. Then we picked up the pace in this segment. We've been pioneering on the use of this waveguide type of solution together with also the previous presenter, and pushing the industry to actually move to this type of solution. And now we are at a stage that we are a well-established supplier for all type of radar, from corner to imaging, from relatively small volume to extremely high volume. And overall, as it was brought up in the previous talk, the advantage has been higher performance, smaller form factor of sensor as you develop above, and overall some other advanced features such as removing the substrate, cooling, or so on. Overall, this journey has basically brought us to create an offering that is very extensive and mature, and essentially we cover all our customer need, and that's why we believe that our solutions are superior. So generally we have, of course, performance-wise, you want to have what you expect out of air-filled waveguide, support full band, support half-wave spacing, field of view, large field of view to high focus beam. Generally, you want also to have it offered to your customer, ready, available, drop-in interface, both for PCB in case of launcher on the PCB, based again on our technology, as well as launcher in package or launcher on package solution from the main chip supplier. We keep a good contact with them to be ready to deploy them. Of course, also some advanced functionality. Of course, when it comes beside the performance, is obviously extremely important that that solution is cost competitive, and we are leveraging a large range of different manufacturing assembly methods, again, thanks to the flexibility and to put together different parts at minimum effort, and of course, target from low to high volumes, commodity to premium, and company launch form factor. Overall, we have in-house production and external production through a large international supplier base. And of course, all our products have gone through automotive standard qualified and have been already trusted and used extensively. So Waveguide solution, they definitely have a lot of advantages, some I touched upon. But they certainly also have some disadvantages of everything. So typically they are, despite being at high frequency, so everything becomes small, they're typically still on the slightly bulky side. They typically have very high initial cost and long lead time. Is a pretty slow process itself. They typically encounter also limitation antenna dimension as you grow larger and larger, or connection to the tough tolerance that remain, it becomes harder and harder. So here on the left, there is actually a picture of an imaging antenna that we've developed for Unders quite a few years ago, but is and one of the few that we are allowed actually to show since the customer has approved that, and that it's an example of an antenna that it's relatively big, it's a relative number layer, it's relatively, it's still very compact, but has, of course, some real estate that is occupying. But in this work that I'm actually presenting, we believe that many of these aspects actually we are addressing and solving. So that's there are good news on the other side. So let me introduce the multi-layer waveguide technology. Here there is a nice picture on the right, because also the eyes once is part. It's a significant difference in how we produce this part. Both in the manufacturing itself as well as how they work. And we believe that is a key addition to our offering, together with the type of solution that we provide today. And overall, it offers some unique possibility, something that was not previously the ability for you to actually have this in a certain product. They give also superior features that were not available in the previous variants, and everything is top on, of course, that is really dependable. We have already tested. This is reached a very mature stage. So to explain the difference between the different types, let me first give a slight overview of a comparison of different waveguide types. These are all air-filled waveguides, so I am excused if I'm not covering sub-3 integrated waveguide or so on. And the reason is that these are kind of the top performance that you get. No dielectric losses and very high performance. So going from the left, there is a typical waveguide type. Then on the center one, could be the typical gap waveguide products. Again, since we have a different set of manufacturing and assembly techniques, there is a range, but this is quite representative of what could be a type of a commodity corner type cheap antenna. And on the right column instead, this new MLW technology. And as you can see, there is on the top, there is an actual picture of some outer, just to give you a sense in reality what they look like. But on the bottom right, there is a kind of a simplified cutout and comparison between the parts. So starting from the left, we have waveguide type of antenna. So typically you stack your waveguide vertically, that because it's the most robust way to do it. And it's generally realized by two molded plastic parts that are metallized afterwards, and that's subsequently are soldered. So that essentially results in a combination of facts that the antenna itself is on the quite thick side. You need two 3D part. You need to coat a plastic part that you injection molded, and you also need to solder. So there is a number of consequences in terms of cost, form factor, and so forth. On the center part, instead, is our more standard solution, which is generally realized by one core part, again, injection molded and metallized, which on top is posed a sheet metal, realizing the lid. Now, the reason for the change is that essentially, due to the robustness of Waveguide technology, it's interesting, we don't need the soldering, so we can lay our antenna horizontally, and we don't need to solder it, and as a result, also, we don't really need a second 3D part. So that's essentially shrinks the number of 3D parts to half, and as a result, also the thickness that from 5 millimeter drops down to about 2 millimeters, or half of it. So we believe that is our kind of typical offering, and that offers a very nice balance and in terms of performance, cost, form factor, and is very attractive. What I'm introducing today is this MLW technique, and is somewhat the logical maybe step forward after this, where all the parts are actually replaced with sheet metal. So now it's 3 layer of sheet metal. The top and bottom one are realizing the EVG type of structure, and the center one is actually carrying a suspended conductor. So this obviously results in another size reduction of half of it. So we are now below 1 millimeter from the original 5. So significantly, as you can see in the comparison, is just much smaller in problem. How does this work? How is made? Well, it's really based on a connection between the design part and the manufacturing. Is a very nice coming together of these very two aspects. So first is, as introduced, metal sheet production, which is how we manufacture the parts themselves. Then it's obviously based on the Waveguide texture, embedding the robustness and ensuring isolation between line. And then again, we also have this feature optional of having a coaxial conductor to actually support a TEM mode propagation type. So here on the right-hand side, there is a picture of a prototype or test structure opened up. So you can see there is a bottom lid layer, a center layer, and a top layer. You can see there is a waveguide port coming from the back, and then routing in and doing a subarray of 3 by, I don't know, 8, 10 slots vertically, and realizing a narrow elevation and azimuth pattern type. So that's a bit how it looks when you open it up. And here there is a exploded view to give you a bit of a better view, so you understand that this is the top and bottom lid are pretty similar with the EVG structure, and then there is this layer in the center, a bit darker in color, which carry the coaxial connector. This essentially creates the fact that we have a coaxial mode when put it together. Performance-wise, it's behaving excellently. Of course, as usual, you have a feasibility to change the characteristic by changing the dimension, but for the worst-case scenario, which is half our interspacing period, we have 0.015 dB losses measured typically. Isolation better than 30 dB if you run 2 lines parallel for 10 millimeter, which you never do, with one single row of pin meter. And overall, it's also non-dispersive, which is a property that it lacks from waveguides. So that's also advantageous. So what does this result? Essentially, as I was saying, in unique possibility. So we have an extremely accelerated, since the manufacturing is very different. There is no tooling involved with this injection molded plastic that is quite time consuming. It's really fast coming to pretty serious product slash the production time, which is extremely interesting because it is generally quite of a bottleneck there. There is a customization flexibility. Obviously, again, it's very agile. It's very cost effective, so we find it competitive for all volumes, and for lower volume, it's a no-brainer. And then it's really breaking also size limitation. Sheet metal manufacturing has not size limitation itself, while injection molded part, they start suffering when you go beyond, significantly beyond 100 times 100, or beyond, you start having, a lot of headache. No problem whatsoever. So that's also a no-brainer for massive imaging radar antenna that we see coming up a lot. And overall, of course, some superior features that are not otherwise available. Since we have this is mostly based on this fully metal coax-based waveguide, you get the same performance in terms of losses and wideband as you would expect from a waveguide. And on top, there is also this removal of dispersion, which essentially makes both routing, but as well as fed antennas significantly more performant with very little squint, and that's enabled essentially higher performance or simpler and lower number of layers and thus cost. And then, of course, remarkably low profile. There is a picture here on the right-hand side. You can see that this is our standard one, which is already the thinnest that you can find. This new solution is almost getting on the paper-thin side, almost below the PCB if you consider the assembled one. And of course, it adds also thermal handling and EMC functionality. Since the body is fully metal, you can also extend in that sense. So it has a lot of pros. And of course, the very important is that it's a trustable solution. And that is actually, we are very happy to be at a stage that we have passed all the gates to get there. So we have, of course, this based on Waveguide Technology, so robustness in terms of tolerance and so on, as you would expect. It is also, interestingly, metallized plastic have typically quite challenging to be recycled, since it's not only a plastic body, but it's also metallized. So sorting and recycling is tough. These are fully metal-based, so they offer opportunity over there. And then finally, of course, automatic quality height. We have thrown over every test for our code, and we passed with very good results. Since there is a fully metal body, then it's very robust. And of course, this is the results of both years of in-house development, but as well as onboarding customers. So we have a leading tier 1 customer that has this fully approved and is on board. So it's very far from being a concept, but it's a solution now. So together with this release of the technology itself, we are also releasing 2 automotive demonstrators for we take this opportunity for you to try. So on the left-hand side, there is the MLW version that I've just introduced, and on the right-hand side is the standard typical Waveguide version on the right. As you can see, the Waveguide version has been actually developed in collaboration with NXP, which they're releasing a demonstrator for their smart TRX launching package chip. So it interfaces directly to that. Between the two, I will not go so much in the details, spare you that. But overall, they are pretty much the same number of channel, interface, size, and everything. The most difference, obviously, is on the technology itself, where we have with 1 core and 1 sheet for the typical MLW, for the typical Waveguide one, and 3 sheet for the MLW one. Thickness, as a result, is 4.5 millimeter for the standard Waveguide one, and about 3 millimeter with the component spacer clearance, but 1 millimeter, below 1 millimeter actually, the MLW one. Antenna performance-wise, they're very similar. We decided to have one slightly bit more broad, the Waveguide one in azimuth, and vice versa, a bit broader in elevation, the MLW, and they have similar performance there. So here are just some measurement, just to give a taste of what you would get. So in the first row is Waveguide, and the second row is the MLW. The first column is the return loss, is one port, 1 antenna, three different samples. So you see a good repeatability between both technologies. Azimuth pattern, the second column, so you can see there is a wider field of view, 3 antennas, very repeatable and very close to simulation. And the same thing for MLW, also a little bit more narrow in azimuth. Elevation, again, 3 measurement. And we have for Waveguide a little bit narrower pattern and a bit wider without nulls in the first zone for the MLW. Just a slight teaser there. That to conclude, essentially we unveiled a new technology for the first time to the larger public. It's an innovative design and a manufacturing concept. We believe it has a significant impact, especially its unprecedented time to market, as fast as you can imagine. Size limits. It has enhanced the performance of Waveguide. Has a minimalistic profile, thermal dissipation, EMC shielding, and of course is robust, trusted, and qualified. It is available now, and at the same time we are also releasing demonstrator available. So that concludes my talk. If you have questions, come and meet us and learn more at booth 2036C. Thank you.